Okay, yesterday we ended with this question. Remember that? Okay. And we found that it would continually accelerate. Good with that? As it experiences an unbalanced force. So, continuation of this question. Why do you think it?
Because of the issue I was also hit on the fact that if the force is equal to zero, then it must not be moving, but he said force is equal to zero, be going at constant velocity. But there's friction. Yeah, but the friction is 10. So if it was going at constant velocity, I don't think so. You could be right. But what I'm thinking is yesterday you said that if your force is equal to constant is not friction. Ignore friction. No, he didn't say ignore friction. He said ignore it on a regular problem.
Is inertia doing what it wants to do when it is moving at a constant velocity?
Yes.
Yes. So, if inertia is doing what it wants to do, then you know that the net force is equal to zero. 100% reliability. Like, that's an always. Moving at a constant velocity, you know the sum of the forces are equal to zero. Correct answer is B. 10 newtons. Because if it was more than 10, what would happen? It would speed up. It wouldn't be balanced anymore. You okay with that? This is a really hard concept to get across. Most people are fine with the fact that something's at rest, that the net force is equal to zero. But moving at a constant velocity, this is kind of a hard thing, and we're going to spend a long time on that. Okay? Everybody good? Tell your neighbor.
Yeah. Tension doesn't matter. I just remember he like tried that. He's like tension. It doesn't rely on the fact that there's nothing.
Correct answer is? Okay. When the fish is hanging at rest, this is the free body diagram, yes? What's another name for force of gravity? Another name for force of gravity? Weight. Okay? So at rest, how does the force of tension compare to the weight? Which one's bigger? Or they're the same? They're the same. Some of the forces have to be balanced, equal to 0. Okay? If you are moving at a constant velocity, you know, beyond a shadow of a doubt, the net force, sum of the forces, the total force, is equal to 0. The forces are balanced. The net force is 0, meaning that it's going to be the same as when it was at rest. Okay, during the speeding up part, no, not the same. But once you are moving and having a constant velocity, then it's equal to 0. I'm going to put you as the fish. You're in an elevator. You hit up. This, as you speed up, but once you get to your max speed, it should feel just like you're standing on the floor at ground zero, like at the bottom floor. Okay? Now, try that the next time, but make sure it's a long, fast elevator. Like, don't go to floor 2, you'll never feel that. But, like, go to floor 10. Okay? Good with that? This is the exact same concept as this previous problem. I just put it from sideways, like the horizontal to vertical. Same concept. Good with that? All right, follow-up question. Tell your neighbor what you think.
What do you know? Did you say C? I said this. Oh.
Correct answer is? Correct answer is B. Okay? This, the number doesn't matter. The fact that it's going constant, that matters. Constant velocity. Inertia is happy. It's doing what it wants to do. Case in point, you're driving in a really nice car. Got a smooth suspension. Okay, you're on an interstate with a nice road. You're a passenger, flipping through your phone. You're not looking outside. You can't hear the engine because you got your earbuds in, okay? And can you tell how fast you're going? You keep going 40 miles an hour, you keep going 80 miles an hour. You don't have any frame of reference outside, you don't know. Your inertia is doing what it wants to do. It doesn't matter how fast it's going. You okay with that? All right. Skip this guy. All right. I want you to draw the free body diagram of the box. I would highly recommend taking notes on this. Highly recommend taking notes on this. okay? Okay, this is step 1 of 5. Okay. Step 2, pick which direction you want to be the positive direction. My suggestion would be my strong suggestion would be to make the way it's moving the positive direction. Moving to the right, make right the positive X direction, make up the positive Y direction. Okay, that was step 2. Not too bad. And I've got, on the next couple slides, I've got all those, what I'm saying written down, so if you want to reference that, it's on campus. Okay. Step 3, this is essential. Remember how in projectile motion I was like saying, hey, the motion and the forces in the horizontal direction are independent of the forces and the motion in the vertical direction? We're going to have that same format, same type of thing, where we're looking at the forces in the X and the Y direction. But I'm going to ask, is the sum of the forces in the X direction equal to 0? Is the sum of the forces in the Y direction equal to 0? Here's what you don't look at. Do not look at your free body diagram to determine that. What you're going to look at is the story. You're going to ask yourself, in the X direction, is inertia doing what it wants to do? Is inertia happy? In the X direction, is it at rest and staying at rest? Or is it moving at a constant velocity? Either of those two scenarios, inertia is doing what it wants to do. Is that the case in this scenario? No, it is speeding up. So if it's speeding up or slowing down, some of the forces are not equal to 0. Does that make sense, what we're looking at? Okay, we're looking at the motion. You determine if the sum of the forces in the Y direction are equal to 0. Is it doing what it wants to do in the Y direction? Yep, it's staying at rest. Equal to 0. Okay? That was step 3. Step 4. We are finding the sum of the forces in the X direction. So what we're going to do is we're going to add up all the forces that are going solely in the X direction. But we're going to keep in mind which ones are positive and which ones are negative. So what forces are going purely in the X direction? Applied force. Is that going positive or negative?
Positive.
Positive. So it's a positive applied force plus, because I'm adding these together, and negative friction. I wouldn't necessarily write it like that. I'm just kind of trying to teach you. That make sense? Okay. And it's not equal to 0. I don't know what it's equal to, but it's equal to something, not 0. So I'm going to set that equal to the net force in the X direction. Sum of the forces in the X direction. Okay? I want you to do the Y. Sum of the forces in the Y direction. You can just write it like this. You okay with that? Rather than this. This is fine. That's more concise. Okay? And we said in the y direction it's equal to, some of the forces are equal to 0, so we set that up equal to 0. Good with that? Step 5, we set that up equal to 0. If it's not equal to 0, what we're going to do is say, we're going to employ Newton's second law and say the net force is equal to mass times acceleration. So what I'm going to do is I'm going to take this guy, and I'm going to substitute in here. Mass times acceleration. So what I get, this is how I'd write it. Applied force minus friction is equal to mass times acceleration in the x direction. And that's your setup. And that's what you're doing tonight for homework. Day 2. Okay. If you needed another worksheet, I got it up here, but we're not done yet. Okay. Remember last couple chapters, when you're doing physics problems, you're like, which equation should I use? And you went shopping through kinematic equations. You are creating your equations right here. These are your original equations that you're going to be using. When I start throwing numbers at you, you're going to use this setup, and then these are going to be your original equations. Okay? So, you see why your free body diagram is essential. If you mess that up, you're like, ooh, that's rough. Okay? Some people, if they embrace these 5 steps, this is on the PowerPoint. Okay, I just talked you through those. Okay, find this chapter easier than the others too. Some people, not all. Okay, these steps are the same steps I teach my second-year calculus physics students. Okay, if you embrace this, this is super powerful. Okay. Good with that? Questions there? I'm going to go through a couple more examples. But those are the 5 steps. Okay. All right, free body diagram of the box. Go. How'd we do? Good? Okay. Now, step 2, pick which way you want to be the positive direction. Make the way it's moving positive, so I'm going to make left positive x and up positive y. Step 2. Step 3. Sum of the forces in the x direction, are they equal to 0? Sum of the force in the y direction, are they equal to 0? In the x direction, you are not looking at your free body diagram. You're looking at your story. Is inertia doing what it wants to do in the x direction? Moving at a constant velocity equal to 0. Is inertia doing what it wants to do in the y direction? The box is at rest in the y direction, not coming off the floor nor going into the floor. It is equal to 0 in the y direction. Okay, again, you're not looking at your free body diagram. You're looking at the story. Asking yourself, is inertia doing what it wants to do? Good? Okay. Step 4, we're adding up the sum of the forces in the x and in the y direction. Now, some of you picked up on my foreshadowing last week. Is tension going purely in the x direction? Purely in the y direction? It's at an angle. So we need to break it up into components. Okay? So I'm not making you do the math yet. I'm just setting this up. The math will come. So you have the x component of tension and the y component of tension. You okay with that? Okay, now do the sum of the forces in the x direction and the sum of the forces in the y direction. Go ahead and finish it on out. How did we do? Okay. On the homework, do not stop with just circling equal to 0 or not equal to 0. If you only do that, that's like 2 out of 10 points. I need all this stuff too. Okay. Good with that? Give me confidence rating. 5, rocking it out. 0, like. Good? All right. Got a harder problem for you. Okay, free body diagram of a car parked on your force of gravity really long. Not really long, but like a couple lines of notebook paper. So if you're on a hill, draw a box angled. How do we do? Okay. Step one. Step two. You pick which direction is positive. Don't draw this. Do not draw this. Here's our y-axis. Here's our x-axis. How many vectors are off of the axis? How many vectors are off the axis? 2. Ugh. Why am I saying ugh? What does that mean? 2 vectors are off the axis. I'm gonna have to do what? Vectors, find the components. Ugh. Okay, check this trick out. This is actually a required trick. I'm going to take the x-axis and tilt it so that the x-axis is now parallel to the hill, and the y-axis is now perpendicular to the hill. Crazy? Okay, that's actually a required step when you're on an incline. So what you're going to do is I'm going to make down the ramp positive x, perpendicular to the ramp positive y. This is why I've stopped calling them horizontal and vertical, because it's not horizontal and vertical anymore. Okay? So that's step 2. Step 3. You are asking yourself, is the sum of the forces in the x direction equal to 0? Is the sum of the forces in the y direction equal to 0? You look at your free body diagram to determine this. It's parked. Inertia is happy, doing what it wants to do. So the forces are equal to 0. There we go with that. Now, now that we've tilted the axis, how many vectors are off the axis? How many vectors are off the black axis? Just 1. Life got a little better. Okay? Now, this next thing I'm going to tell you straight out memorize. Don't tell you to memorize many things, but this is one of them. Whatever this angle is of the hill, that's the same angle between the new y-axis and the force of gravity. Okay, between the new y-axis and the force of gravity, same angle. Now, I will never ask you to prove this geometrically. I'm just going to do that for the people who are like, well, why? Here it is. Only time I'm doing this. this hill is parallel to this black x-axis. This line here is parallel to this blue dashed axis. This angle and this angle are congruent. Alternating interior angles or something. Okay. This angle is 90 degrees. This angle is 90 degrees. This angle and this angle are both complementary to this angle, so this makes this one congruent with that one, therefore congruent to that one. Never going to make you do that. Okay? Just memorize it. Okay there? So, all right, so I need to break this force of gravity up into components. When I was in high school, I did this wrong. I want you to pick out which is the correct way to do it. That's one way. That's the second way. One of those is correct, one of those is wrong. Tell your neighbor which one is the right one and tell them why. Correct answer is red or green. Red is good, green is bad. Okay? Here's why I missed lots of points with this. Okay? Here's why green is bad. Two reasons. Number one, the force of gravity is what you're breaking up into components. This should be the hypotenuse. It should be the longest side. Second reason is your x component needs to be parallel to your x-axis. Okay? Don't do the green. Okay? So, here's our F, G, Y. Nope, F, G, X. Right? F, G, X. F, G, Y. Okay? All right. I want you to set it up. Some of the forces do step 4 and 5. Some of the forces in the x direction, some of the forces in the y direction. Go. How'd we do? Good there? Questions? What's the confusion?
So like, say something like wasn't on an incline, and like a box that's like not moving, I guess.
Uh-huh.
And well, like it was like problem 1 on the worksheet, the free body diagram.
Yep.
And it was like something how it was still moving, but there wasn't anything like pushing it, so there was no applied force technically.
Right.
So then, what's stopping it from, like, what slows it down? Like, even if it's not on an angle like this?
Yeah, because you made it move, you kicked it,
Oh, okay.
and you made it move. Okay? All right. I want you to do this one, take it all the way, start to finish. Give you a 3-minute head start. Remember to include friction. Make sure your free body diagram is correct. That would be tragic. Okay, some of the force in the X direction is not equal to 0 because you're speeding up. Check this out. Some of the forces in the Y direction are equal to 0. Yes, they are equal to 0 because the Y-axis is no longer vertical. The Y-axis is now tilted perpendicular to the hill. You're not leaving the hill, nor are you digging into the hill. It's at rest in the Y-axis. Everybody see that? Okay, so it's equal to 0. How do we do? Good there?
On the MA, do you have to put the subscript X?
You don't have to. Good? That's what you're doing for homework. Okay? Got one more conceptual question for you. Following on, backtracking. Last question. Oh, sorry. That's advocate a little bit more. Tell your neighbor what you think. Tell them why you think it.
I feel like I want to say A. Like, you know what I mean? Like, oh, this portion just stops. Like, think about like, perhaps I give you that hydrogen. Oh, never mind.
Okay, ready?
You're getting one. I would join you.
Okay, we're speeding up. Going constant. Okay. What's the sum of the forces right here? 0. So is inertia doing what it wants to do? Yes. What was it doing right before this one turned on? It was moving. So it's going to continue moving at whatever speed that was. Good with that? In order to make it stop, you need this momentary, like, wham, force. Okay? If this was 11, then it would slow down gradually. Have a great rest of the day.